Hey Starship addicts, my name is Zach Golden and welcome to part 2 of this CSI Starbase deep dive investigation. I hope all of you are ready for today's episode because it's finally time to discuss how SpaceX is going to get past one of the largest and most important obstacles that they have encountered as they approach the first ever Starship orbital flight test. The temporary solutions that SpaceX engineers have come up with to enable themselves to safely perform a 33-engine static fire test will not work during an actual launch attempt. This is an incredibly complex situation, so I'm going to try to cover every detail as thoroughly as possible. With that said, we have a lot of ground to cover today, so let's not waste any more time and jump right in.
Welcome to CSI Starbase.
As a quick refresher, in part 1 of this deep dive investigation, we peeled back some super heavy curtains so that all of you Starship fans at home can get an inside look at what is going on behind the scenes as SpaceX prepares for the first ever 33-engine static fire test on the Orbital Launch Mount. To put it plain and simple, SpaceX's #1 priority right now is doing whatever is necessary to prevent explosions from occurring on or around the Orbital Launch Mount. The second major objective is to limit the potentially catastrophic damage sustained by the vehicle and launch system in the event that they fail to prevent the aforementioned explosion from occurring. We discussed the Orbital Tank Farm methane recovery system, which is one of the key components of this operation. Constantly venting out methane gas would present a huge explosion risk during the propellant loading process of the booster and Starship. If everything is functioning properly, the release of large volumes of methane gas into the surroundings will only occur during spin prime testing of the Raptor 2 engines. Spin prime tests are critical for verifying that engines are functioning as expected before attempting a static fire test. During the spin prime test, it is necessary and, as far as I can tell, unavoidable for a large cloud of liquid methane to be ejected from each of the Raptor engines as they spin up the methane turbopump and fully prime the system. The reason the testing anomaly that occurred on July 11th resulted in a supersonic detonation instead of a slightly less damaging explosion or just a massive slow-burning flame was due to the presence of a large amount of evaporating liquid oxygen under the table before the initiation of the 33-engine spin prime test. The more oxygen available to react with the methane, the more severe the explosion will be. To reduce the amount of oxygen under the launch mount and booster, SpaceX has chosen to take a two-pronged approach. First, they installed the Firex and Detonation Suppression System, or FDS for short, which we discussed in this CSI Starbase special report. The FDS, which is often confused with an ultra-weak water deluge, is designed to reduce the oxygen levels in the ambient air as much as possible in order to slow down the rate of combustion should the methane cloud manage to find an ignition source. Second, SpaceX has installed a temporary Raptor chill collection system to divert away the liquid oxygen that was previously deposited directly underneath the engine skirt during the chill down sequence. The collected liquid vapor mixture is sent over to this pit decently far away from the launch mount where it can no longer react with the methane cloud during spin prime tests and static fires. This is a temporary solution because it requires 33 flex hoses to be directly connected to each of the booster's Raptor engines. Launching with these installed would result in the hoses being ripped free from the collection pipe fittings on the OLM or on the engines themselves. Either way, it's pretty clear that that's a no-go for the actual orbital flight test.
So what are they going to do? We haven't seen them working on any other permanent solutions, right? Well, what if I told you that SpaceX might already have a solution for this, but for some reason they aren't using it? Between me and you, I think they might even be afraid of it. I should say that quietly because I'm pretty sure this tower can hear me. This is the only system on the Orbital Launch Mount that I have never once seen in action. I want to warn all of you that what I'm about to tell you is highly speculative in nature. There is a strong probability that some of the information you're about to hear could be incorrect. As you can tell, the Orbital Launch Mount is an extremely complicated machine, so take everything that I say with a huge pinch of salt.
Ever since the day I learned that the Orbital Launch Mount Raptor QDs would be responsible for starting the outer 20 engines on the Super Heavy booster, I've been obsessed with trying to figure out how this system works. At that time, I didn't know enough about the Raptor engines to begin identifying individual pipes or determine which direction all of the different gases are flowing in. But there was one thing that I was 100% convinced of. There is zero chance SpaceX is going to be venting liquid oxygen from the Raptor chill down sequence out of the side of the booster the way that they do with the Starships on the suborbital test stands. Looking at the Raptor quick disconnect, I was confident that 5 out of the 6 ports would be used for injecting gases into the engine, and at least one of the 6 ports would be used as a drain to collect the liquid oxygen during the Raptor chill down sequence. Some of you may have even heard me say this before during the live stream commentary on the Lab Padre channel before the day of the Booster 7 explosion. My rationale for this came from looking at footage from all of the past Starship launches, but in particular SN15's suborbital test flight. You can see how heavy the flow gets when it's deep into the chill down sequence and liquid oxygen begins flowing out of the 3 vents. I couldn't imagine multiplying this by 11 on the Orbital Launch Mount. Every pre-launch sequence would look like the SN11 FTS, flight test. You know, the one where there was so much fog we couldn't even see what was happening. RIP SN11. So, just as we do with everything else, I started looking out for signs that SpaceX would instead collect the liquid oxygen pre-chill venting and then divert it to another location. I didn't have to look too far to find out what I was looking for. There was one major feature on the Orbital Launch Mount that I've never mentioned in any of my past deep dive investigations. This feature was one of the first ones added onto the table, and I believe it is now the last to be used. If you follow CSI Starbase on Twitter, then a lot of the confusing tweets that you may have seen over the last 3 months are hopefully about to start making a lot more sense, starting with this. It took a really long time for me to identify these components mounted in the middle of this manifold. It's not something that I ever came across in my time in the oil and gas industry. Or at least that's what I thought at the time. It wasn't until I recruited Special Agent JT that I finally was able to determine what these devices are used for. What you are looking at here is a very important piece of equipment known as a flame arrestor. There are many types of flame arrestors out there, but this one is designed to be installed in line between 2 pipe flanges. It is attached using 2 large Victaulic clamps on either side. There is also a third clamp in the middle to hold the 2 sides of the flame arrestor together. This allows for the internal components to be swapped out should the need ever arise. As you can see, there are 4 of them located in parallel. So the flow would come in from one side, split off into the 4 pathways, and then recombine again on the other side. The problem is, we don't know which direction the flow is traveling. To figure that out, we should probably discuss what a flame arrestor is, and then try to determine how it might be used in this situation. According to Paradox Intellectual Properties Inc., a company based out of Florida who claims to be one of the original creators of this technology, a flame arrestor is a critical safety device used in vapor management systems. They are typically used to protect storage tanks or systems with short pipe lengths. The main goal of this device is to stop the propagation of flames inside of the pipe. It accomplishes this by passing the flame through a set of filter discs, which are basically a circular mesh of thousands of small pipe channels. This increases the overall surface area for the heat energy of the flame to be dissipated through the walls of the channels so that by the time it reaches the other end, it's cooled to the point where the flame has been extinguished. The most important thing to note here is that the only reason to have an inline flame arrestor is if there is a risk of mixed gases passing through the system. If pure methane or oxygen was being delivered to the launch mount, then there shouldn't be any reason for a flame to end up traveling backwards through this pipe. Just like most fuels, methane needs to have a source of oxygen or else it won't ignite. On the opposite side of the spectrum, if the flow was made of 100% oxygen, well, I think that one speaks for itself. So this means that the gas is being collected from the launch mount, not supplied to it. In order to fully understand how this would be applied here, we need to determine which direction is the protected side and which direction the flame is coming from. The easiest way to do that is to pick a direction and start tracing out this pipe system. Let's go to the left side of the manifold first. Here we can trace the pipe straight down through the walkway, and then from there it goes back towards the inside of the table and then is redirected upwards through the floor where it reemerges inside of the structure. If we look at this picture taken from Nick and Sweeney on the day the table was rolled to the launch site, we can see each of the 7 circular pipe manifolds that existed on the inside of the launch table. Now, take a look at the largest one located on the bottom of the table. When we superimpose this image with one of the flame arrestor manifolds that we were checking out earlier, you will notice that these pipes are nearly identical in diameter. I think we have ourselves a match. In my opinion, the fact that this pipe is so much larger than all the others inside of the table is another sign that it's a collection manifold and not a supply. Transitioning from the small diameter of the Raptor chill tube up to the large diameter of the collection manifold will cause a decrease in velocity of the flow of liquid oxygen in the pipe. Decreasing the velocity will result in a drop in pressure inside of the manifold, which helps to facilitate faster boil-off of the liquid. Alright, now let's look at the other side of this flame arrestor manifold to see where the expected Raptor chill venting would end up being routed to. If we follow it down the leg of the orbital launch mount and then transfer up to the aerial view, we can see that the pipe in question is situated in the middle of the liquid oxygen and liquid methane supply pipe that we identified earlier. It follows those pipes all the way back to the orbital tank farm. Once it reaches the fluids bunker, it's really difficult to tell what happens to it. Based on my limited understanding of the interior of this structure, I have a feeling that this pipe enters the bunker and then splits off in either direction before it exits out of the side of the building and then ends in a bullnose vent located on the back side of the building. Again, we can't prove that these outlets are connected to the system, but what we do know is that we have never once observed any venting coming out of these two locations. When we return back to the basic principles that we've learned, the outlet of these vents would be considered the protected side of the flame arrestor. But so is the pipe that runs along the wall inside of the building and the entire pathway between the fluids bunker and the orbital launch mount where the actual protection system is located. Here's the hardest part of this to understand. If this is an oxygen collection system, then why is the flame arrestor needed? Well, the only reason I can come up with is that for some reason there is a risk of methane bleeding into the Raptor Chill exhaust flow. But if that's the case, then where is it coming from? I've been looking for proof of this for a long time, but it's very hard to find. Initially, I believed that there is a possibility that the source of methane could be the actual Raptor QD panel itself. The connection between these two is not what I would consider a hard connection. A hard connection is something that actually has some sort of locking mechanism. This is more of a press fit. So I imagine there is some potential for leakage when the high pressure gases are being injected into the engine during startup. These gases are being injected at relatively high pressures, somewhere between 3,000 and 6,000 psi, which is equivalent to 200 to 400 bar. The Raptor Chill collection pipe, on the other hand, is probably just about as close to atmospheric pressure as it gets. Honestly, I wouldn't be surprised if there's actually negative pressure inside of here, creating a vacuum to suck the flow of oxygen out of the engines. This would require some sort of suction pump to be used, which would most likely be located inside of the fluids bunker. As of yet, I haven't seen any evidence to support this, but I think it's important to mention it as a possible design consideration. This is important because if there was negative pressure inside of this pipe, then any leaked gases coming out of the other 5 Raptor QD nozzles would surely be sucked in through this one. While this theory does seem plausible, there's another one that I like even better. For this one, we're going to need to take a look at this 3-engine preburner test performed by SN8 just over 2 years ago. Keep in mind, a preburner test is basically the same thing as a spin prime test, except it includes a massive fireball at the end. After SpaceX switched to the Raptor 2 engines on the current generation of ships and boosters, preburner tests are no longer performed, but there is still information that we can gather from the version 1 Raptor engines. I'm going to slow this down so we can point out a few important observations. During the last few seconds leading up to the start of a preburner test, there is a steady stream of liquid oxygen flowing out of the 3 Raptor Chill vents. The flow looks similar to a typical garden hose without a nozzle on the end. The moment the preburner test is initiated, the stream of liquid oxygen coming out of the Raptor Chill vents is suddenly forced out horizontally in a quick burst. Before it even has a chance to begin falling to the ground, a huge flame is ejected out of the bottom of the Starship. This flame starts off below the vehicle, and as it slowly reaches out from beneath the test stand, it appears to come in contact with additional methane that was already lingering in the air. In my opinion, this residual methane present in the surrounding air is most likely coming out of this Raptor Chill vent. I think that during the spin-up process, the location inside of the engine where the bleed-off vent is originating from switches from being 100% liquid oxygen to being a mixed flow. It then remains a mixed flow until the Raptor engines shut down. Once the engine shuts down, it immediately returns to being a pure oxygen flow. Initially, I wanted to go through a long explanation of how exactly this mixed flow could make its way to the Raptor Chill vent using this Raptor engine diagram. I spent a lot of time dissecting Elon's explanation of the Raptor 2 engines in the recent Everyday Astronaut tour of Starbase. Unfortunately, I think I would lose a lot of people along the way, so I removed about 10 minutes from this episode because I realized it's kind of an unnecessarily deep rabbit hole for us to go down right now. If enough of you are interested in hearing more about how this is possible, then let me know in the comments and maybe I'll do a special Q&A livestream soon to answer all of your lingering questions from parts 1 and 2. Anyways, back to the point. I want to examine this preburner test again, but this time I want you to think of it as an aborted engine startup. So let's compare it to a static fire test side by side. Notice how in both situations, the flow from the Raptor Chill vent increases dramatically for a brief moment right when the spin start occurs. After the engine has ignited, we don't see any Raptor Chill venting, but as soon as the engine's cut and the smoke clears, we can see that the Raptor chill has resumed again. When we look at the pre-burner test, we can see that the LOX chill vent resumes pretty much immediately after the spin-up process is complete, because the ignition sequence has technically been aborted. Another interesting observation here is the moment the pure liquid oxygen venting resumes, the fire above the engine skirt immediately vanishes. There is still a fire present below the skirt, however, and that fire is consuming oxygen at such a high rate that it actually begins to create a vacuum as it begins pulling all the available oxygen out of the surrounding air and back up into the bottom of the engine skirt. After making this observation, I think it's probably a good thing that the Raptor chill venting is coming out of the side of the ship instead of directly beneath it. If the engine chill was instead vented underneath the Raptor engines, then the intensity of this fire from the pre-burner test would have likely been much greater because the flame wouldn't have to wait for the oxygen to be pulled in. It would already be right where it wants it to be. Too much oxygen, and this flame turns into an explosion. With 3 engines, the result of doing something like this might not be that damaging. But if you multiply the amount of methane and oxygen involved in this situation by 11, in other words, going from a 3-engine test up to 33 engines, well, we already know what happens if you do that. To prevent this, SpaceX would instead collect the Raptor chill flow via one of these 6 ports in the Raptor QD. This dramatically decreases the risk of explosions that can occur during spin prime and static fire testing. So here is where the problem arises. Igniting all 33 engines during a static fire test or during the actual launch is guaranteed to be an incredibly violent event. If the Raptor QD connection is compromised at all during the moment of ignition, then all of a sudden the Raptor chill flow is potentially being exposed to an open flame. If this happens, there will now be a flame traveling through the flex hose on the Raptor QD and then into the collection manifold on the bottom of the table. What happens next is best explained by this video from Elmac Technologies, which I have linked in the description if you would like to review the evidence used in this investigation for yourself later.
Whenever a flammable gas or vapor is mixed with air, there is the potential for an explosion. Accidental ignition of the flammable mixture will initiate a flame which, when confined in a pipe or vessel, will accelerate through the unburned mixture, driving the flame front forwards. Phase 2. Deflagration. The rapid increase in the temperature and volume of the burning mixture, together with conditions that increase turbulence in the system, such as changes in size, roughness, or bends in the pipe, etc., results in a pressure wave that travels ahead of the flame. This phase is typically characterized by subsonic flame speeds of several hundred meters a second, with peak pressures in the range of 10 bar. The flame can accelerate from a slow to a fast deflagration. Phase 3. Unstable detonation. If the flame continues unchecked, and if there is a sufficient pipe length, then due to flame front instabilities, it will undergo a sudden and rapid transition from deflagration to detonation. This deflagration to detonation transition, often referred to as a DDT, is characterized by supersonic flame speeds in the range of 1600 to 3000 meters a second. And a shockwave that is now coupled to the flame front and creating enormous peak pressures, often well in excess of 100 bar. Phase 4. Stable detonation. Following a DDT, an unstable detonation will degrade to a less severe stable detonation. However, due to the gas mixture and changes in the pipeline geometry, further unpredictable DDTs may occur, resulting in what is known as a galloping detonation. The location of the incredibly destructive forces of an unstable detonation cannot be predicted with any certainty. It follows, therefore, that the use of a stable detonation arrestor in isolation is not suitable, as it would not stop a detonation in the DDT phase. Accordingly, and in order to ensure maximum protection from worst-case scenario explosions, Elmac Technologies strongly recommends that one of its patent-protected, unstable detonation arrestors be fitted in all systems where a detonation could occur. These unstable detonation arrestors also provide protection against stable detonations and deflagrations.
So, based on this information, I think it's safe to assume that a detonation is far more damaging than a deflagration. If the pipes are not able to withstand the destructive forces now being generated inside of them, they will fail. In this case, failure means an overpressure event occurring within the pipe, resulting in a rapidly unscheduled disassembly. Keep in mind that this pipe is located in between the liquid oxygen and methane main supply pipes. So a DDT event occurring in this area would be equivalent to a 100-meter-long FTS strip being laid from the top of this leg all the way over to the inside of the fluids bunker. If the Raptor chill pipe explodes, the resulting shrapnel will pierce both the liquid oxygen and liquid methane supply pipes, and at that point, the entire volume of the void space inside of the concrete culvert will be instantly filled with a mixture of liquid oxygen and liquid methane. If that happens, well, it's not really fun to imagine what the result of that would be. The only thing preventing this from occurring is a properly designed flame arrestor element.
The size of the channels that this flame is traveling through is a critical design consideration. The diameter of these channels is dependent on the composition of the mixed flow passing through the flame arrestor elements. Think about it this way. If the concentration of methane bleeding into the Raptor chill collection manifold were to increase, the temperature of the internal flame will increase as well, since there is now more fuel available to burn. If the heat generated from the flame increases, then the diameter of these channels must decrease in order to maximize the cooling capability while also being careful not to restrict the flow as it passes through. The reason I mentioned the possibility of flow restriction is because I was unable to find examples of these being used in potential cryogenic applications. I think this might be an important thing to consider, given that before the spin prime, static fire, or launch event, these pipes are going to be filled with ambient air. If liquid or gaseous oxygen gets introduced into the pipes before the humid Texas air is purged out, it could cause ice to form inside of the flame arrestor element, significantly reducing their performance. If that occurs, they would fail to do their job, and we now have ourselves a major problem. So we better make sure we have enough of them in order to prevent this from happening. Whether the reasoning for this is correct or not, that's exactly what SpaceX did. Upgrade the size of the handcuffs used to arrest these flames. By December 21st of 2021, the 4 parallel flame arrestors had doubled in size and now featured 8 flame arrestors arranged in 2 sets of 4. While it was in this configuration, I had some concerns that by the time the flames reached this manifold, it might be too late to prevent the deflagration to detonation transition from occurring, especially if the flame originates from the opposite side of the table, which would give it a much longer distance to travel before reaching the flame cuffs. For months, I was anxiously awaiting the initial testing of this system so I could finally see it in action. Unfortunately, Booster 4 never ended up performing engine tests of any kind during the 4 times that it was on the Orbital Launch Mount. Well, unless you count the igniter tests that we mentioned on the Booster 7 explosion deep dive episode. Without performing a spin prime or static fire, there would be no reason to expect to see this function tested. On March 24th, Booster 4 was lifted off of the OLM for the last time and quietly entered into an early retirement. I have a feeling that part of the reason SpaceX never attempted a static fire test with Booster 4 was because of this flame arrestor system. From what I can tell, even after the upgrades, SpaceX engineers were still not satisfied with its design. Before Booster 4 had even been removed from the OLM, the flame arrestors had already disappeared from the side of the structure. Many people believed that these were gone for good because we never saw a return in the 9 months since this happened. But that's not the case. They are definitely still around. If you watched the Booster 7 explosion deep dive investigation, then you might remember that when Booster 4 was taken off the OLM for the last time, SpaceX was already in the process of retrofitting the Raptor QDs in order to be compatible with the new design and attachment angle of the Raptor 2 QDs on the next generation of super heavy boosters. As a reminder, the entire Raptor quick disconnect system had been removed from its frame, as you can see here. But there was also another important detail present in this image. If you look at the bottom of the doorway, you will notice an L-shaped pipe which is waiting to be mounted somewhere inside of the table. It just so happens to be the same size as the Raptor chill collection manifold visible behind it. If we look at these aerial pictures from the time it was removed, we can see additional L and T-shaped pipe fittings waiting to be installed inside of the table as well. There are 10 of each. Let's take a look inside of the OLM using the Starbase simulator game as a reference, and I'll show you what's happening here. I believe the 90-degree elbow section is connected to the collection manifold inside of the table. It runs from the manifold over to the back wall and then turns up towards the ceiling. On top of that, the split T-shaped pipe is installed. Because this is mounted directly behind the hold-down clamps, the split T-fitting is used to allow 2 flex hoses to be attached to either side. From there, it can be connected to both Raptor QDs on either side of the hold-down clamps. This is easier than having individual branches for all 20 of the outer Raptor engines. On the outside of the launch mount, the pipe that was originally connected to the 8 flame arrestors was routed inside of the table so it could be connected to the outlet of the collection manifold ring.
But what about the flame arrestors? What happened to those? What if I told you that instead of using 8, SpaceX has upgraded yet again, except now they're using 10 flame arrestors? So if the system is even larger than it was before, then why is it so difficult to locate? Well, in order to find these flame arrestors, you have to be on the lookout for one of the key features that I mentioned earlier in this episode.
Remember the 3 Victaulic clamps that are used to attach the flame arrestor to the manifold? This is the feature we need to look for on the inside of the table. When we zoom in on this image and peek through the doorway, we can see 1, 2, 3 Victaulic clamps behind the 2 shielded power cables. There's another one right here, which is probably the easiest out of all of them to locate. The others are much more difficult to find. But thanks to the massive library of photos on Starship Gazer's Patreon, we were able to look through each of these open doorways from every possible angle. This allowed us to find most of them, but not all. However, we are confident that there are 10 of them. So, these 10 flame arrestors are mounted in between the L and T-shaped pipe sections. Each flame arrestor is now responsible for handling 2 Raptor engines. Because it's located just after the attachment point of the 2 flex hoses, it's now much closer to the source of the flame. This means less time for the flame to transition into a Phase 2 deflagration or Phase 3 DDT.
One of the biggest questions here is, what was the plan for the Center 13 engines? I believe these may be collected through the booster QD, but this is extremely difficult to prove. But on that note, so is pretty much everything else I just said about these flame arrestors. I think we need some concrete evidence that SpaceX did in fact have plans to collect this Raptor chill venting from the very start. I mean, if it wasn't already in the plan, then how did they react so quickly to develop the temporary solution that we talked about in part 1 of this investigation? They installed it so quickly after the Booster 7 anomaly that it was almost like they've done it before or something. But the only other time they've tested engines on a booster was with Booster 3. Is there any chance we can find some evidence that supports these claims by looking at that test? Well, certainly if we're looking for something related to the Center 13 engines, that would be the place to start. Booster 3 was a special booster for many reasons. My favorite thing about Booster 3 is that in order to pull off this 3-engine static fire test, Booster 3 had to be jerry-rigged in a way that not even Starhopper could compete with. I think it's worth reviewing some of the things that SpaceX had to do in order to perform this static fire test on Booster 3.
First, since Booster 3 was going to be tested on the suborbital pad, they had to install an adapter to raise the mounting height to account for the 3 underhanging engines. The adapter didn't have any pre-positioned clamps like the transport stand, so this guy had to position it perfectly, alone, with his bare hands. Without clamps to lock the skirt into position, the booster had to be welded down to the frame. SpaceX hadn't designed a QD panel for the Super Heavy booster yet, so adding fuel to the LOX and methane tanks was done through a direct connection using 2 large flex hoses. The tank pressurization had to be done through a direct connection as well. Except for this, they made use of the incomplete autogenous pressurization lines on the side of the booster. Booster 3 was never going to do a long enough duration static fire test to require back pressurization of the tanks, so there was no need to connect the autogenous pressurization lines. The problem is, something had to be done with the gas that would otherwise be directed to the LOX and methane tanks, so this meant SpaceX had to modify 3 Raptor engines for this custom job. Jack Byer from NASA Spaceflight caught an image of one of them before it was sent back to the testing facility in McGregor, Texas on July 24th to receive the necessary alterations. Boca Chica Gal was on site when they returned 3 days later, so luckily we were able to compare them to see if there were any noticeable changes. It turns out there were a lot of them. I think it's a good idea to quickly point out some of these changes, so let's do that starting with this pipe right here, marked in red. This is the methane autogenous pressurization line. This pipe is used to divert a portion of the hot gaseous methane back up into the booster fuel tank after it's been vaporized inside of the engine valves. Apparently, methane autogenous pressurization is an optional feature on the Raptor engines. Since it wasn't needed, it was removed and a cap was placed where the pipe would normally be located. The sensors inside of the engines will more than likely automatically adjust for the extra methane that will now be present in the system. Next, the pipe shown here in blue was removed as well. This one has been identified as an inerting fluid based on the colors on the attached sticker label. I'm assuming this is nitrogen, which is used for purging out the engines after they are shut down. The only reason I can think of to remove it is if they were only storing helium in the 2 COPVs on the side of the booster. Speaking of that, doesn't it look like there is supposed to be a third one mounted to the right of these two? This could be the position of the missing nitrogen COPV tank, but that's just a guess. Anyways, the helium gas needed to spin start the engine is supplied by this pipe right here. Looking at the before and afters, that one is obviously not changed. Another immediately noticeable change though was the large pipe highlighted here in green. This is the autogenous pressurization line for the oxygen side. Instead of removing it, a curved fitting was added onto the end of the pipe in order to divert it to another location. Returning to Booster 3 on suborbital pad A, we can see a pipe sticking out several meters from underneath the test stand. This pipe is the combined exhaust vent for the 3 diverted autogenous pressurization lines for the LOX tank. When we watch the actual static fire attempt from the view of Lab Padre's Nerdle Cam, the autogenous line is venting from the side of the test stand leading up to the engine startup. At the moment of ignition, the gaseous oxygen quickly shoots out in a jet before disappearing behind the rising wall of flames. Looking at it from the other side, we can see...
Wait, what? Oh, wow. Is this the Raptor chill venting? Oh man, and it's coming out of the side of the test stand? Well, I guess that explains why this looks so familiar. Turns out this was not the first time we saw Raptor chill venting being collected and diverted elsewhere. That title actually goes to Booster 3.
Thanks to the lack of an engine skirt and the design of this adapter for mounting it to the test stand, we have a clear line of sight on some very important details. Now that we know what to look for, looking back at the images from Starship Gazer, we can see the flex hose connected directly to one of the drain pipes on this engine and then being routed over to the pipe on the side. There is no Raptor chill vent on the side of the booster like there is on the Starship, so without this, the only other option would be to dump it directly beneath the engines.
So, I think it's pretty clear that SpaceX was aware that this was something they should probably avoid doing. Yet they tried it anyways on Booster 7. This might sound like I'm throwing shade at the team of insanely talented engineers working just downstairs, but that's not my intention. The truth is, when you're developing a brand new rocket, especially one this advanced, mistakes are bound to happen.
Yeah, and if you look at like the various reasons, like where we blew up starships, like, and you looked at the risk list, none of the reasons it blew up were on the risk list.
Really?
Yeah, there was like no. Maybe you could argue like one of them maybe was on somebody's risk list, but it wasn't brought up beforehand.
I believe the exact event witnessed during the July 11th explosion was something that was definitely on their list of possible hazards. Without the permanent solution in place, they probably did some risk assessment and came to the following conclusion. Although the severity of the event, if it were to occur, could be extremely high, the probability of it actually happening was incredibly low. There should be no sources of open flames or machinery prone to shorting out and creating sparks anywhere near the launch mount while methane is being used during testing. So therefore, the only possible risk would be an accidental igniter test. But as I mentioned on the Firex and detonation suppressant episode, even if the computer accidentally commands for an igniter test to occur at literally the worst possible time, there are safety features in place on every single system of the launch mount to stop them from being used no matter what the code tells it to do. Anyways, we may never know what truly happened there unless SpaceX decides to tell us one day. But the important thing is, they are taking all of the necessary steps to prevent it from happening again. One of the last important questions that we have to answer is, if everything I'm saying is true, then what is stopping SpaceX from using this system right now? I think the answer to this is contained within the same tweet from Elon that I mentioned in part 1 of this investigation. With that said, there are sensors in place to detect this, and more coming in the future. Initially when I heard this, I thought to myself, I don't really think you need a sensor to tell you that there's 7 tons of methane in the air underneath the launch mount. But again, realizing that Elon is usually super careful with his words, I had to look into this more and see if I could find those sensors.
I was able to locate a total of 5 new sensors added to the exterior of the launch mount since July 11th. The first can be seen here on this Raptor chill pipe. Notice how the inlet to the collection manifold has 2 pipes entering from either side of the T. There are only 2 inlets on the entire manifold that have T-fittings attached to them like this. I think one of the pipes entering here is a Raptor chill collection line, and the other one is a pipe that feeds back into the launch mount where there is a sensor that measures temperature, pressure, and most importantly, methane content on a parts per million scale. It makes sense to collect each of these data points on the far side of the manifold. The engine in this position has the greatest distance to travel before it reaches the T that goes down the leg of the opposite side of the table. If we go back to that side, you might remember when I mentioned that there was a sixth inlet on the manifold that is not connected to any of the engines. It goes up into the table like the previous one. This one will be measuring the flow going directly into that T fitting. To the left of that, there is another port on the manifold that also has a T fitting and a pipe going up into the table. This engine will likely have a lot less resistance that it has to fight against in order to push out the Raptor chill fluid because it's the closest to the downpipe and has the least amount of distance to travel.
I think that taking measurements in all three of these locations is extremely important for SpaceX, and it's probably not just a simple once and done process either. But the question of the day is, why? Why does SpaceX need to collect this kind of data on a system that we all agree by now is temporary? If you've ever watched a Raptor engine static fire from the McGregor test facility and really paid close attention to it, then you may notice that SpaceX is clearly making tons of changes to the startup process of these engines as they continue to dial in their performance. Each of these tweaks could have an effect on the concentration of methane found in the Raptor chill vent flow and the amount of time it takes for it to clear out of the system once the pure liquid oxygen venting resumes after the engines are shut down. So having tons of measurements to go off of before you settle on a final flame arrestor design is probably a good idea. Of course, as always, I wouldn't make a huge assumption like this without having at least a small piece of evidence to back these claims up. So let's look at how one of the recent tests of the temporary system went now that we finally have all of the background information out of the way. It's time to watch the Booster 7 7-engine static fire test, and this time I want you to pay attention to the collection pond for the Raptor chill venting.
As a reminder, this is what it looks like when Raptor chill venting has reached its peak. This collection basin is really not that far from the Orbital Launch Mount. With the size of the flames produced by the booster during this test, maybe we can see some important signs here. Those of you who follow CSI Starbase on Twitter might remember when I posted this video a few weeks ago in response to a tweet from Elon. In this footage from Lab Padre's NerdleCam, you can see that as the flame from the static fire reaches out towards the collection basin, the pool of liquid that is slowly boiling off does not catch fire as the flame from the static fire finally reaches the pit. This again confirms that the main component of Raptor chill is in fact liquid oxygen. But as the smoke clears, you will notice that a vortex has formed over the collection basin. I'm definitely no expert on this, but I believe this vortex was caused by a cloud of invisible methane that has only just now reached the outlet of the combined Raptor chill vent and is now rising into the air. As the flame from the static fire reaches the invisible vapor cloud, it immediately ignites it. In my opinion, there's probably very little oxygen in the air at this moment due to the exhaust from the Raptor engines only just now clearing the area, so what little oxygen is available is consumed pretty much immediately. As a reaction begins to run out of oxygen, just like all fires, it begins pulling it from anywhere available. In this case, the highest concentration is directly below the flame inside of that pit. So I believe the vortex is caused by that updraft of boiled off oxygen gas getting pulled up into the flame. And of course, as the engines shut down, the flow inside of the pipe returns back to being 100% oxygen flow, and then the moment it reaches the pit and the last of the methane being released has been consumed, the vortex vanishes.
One of the reasons I've delayed the release of the second part of this episode was to observe a few more static fire attempts to see if this phenomenon would be repeated.
I usually try to confirm things before speculating on them publicly. Unfortunately, as SpaceX increases the number of engines being fired in these tests, the size of the exhaust plume and debris cloud is increased as well. In both the 14-engine and 11-engine static fire tests, the exhaust plume had a significantly greater spread, which reached beyond the edge of the Raptor chill collection pit. If there is a vortex forming inside of this cloud, there is no way for us to see it occurring. Part of the reason this is a difficult situation to discuss is the fact that it's still ongoing. Until we see SpaceX transition from static fire testing mode over to the launch configuration for Stage 0, we won't be able to know for sure if the last 40 minutes of speculation is correct. I think that once SpaceX finally performs a 33-engine static fire test, they will have gathered enough data to allow them to become more confident with using the permanent solution. When that day arrives, I believe we will see the temporary Raptor chill collection pipes removed from the launch mount.
They will be removed at some point. That's a for sure fact. But what happens after that is the question. Will the Raptor chill venting be relocated to the orbital tank farm as I'm speculating? Or will SpaceX simply revert back to venting the liquid oxygen below the vehicle and use the Firex and detonation suppression system during the Raptor chill sequence to more quickly disperse the liquid oxygen as it's raining down from the engines? I'm sure that by now, all of you understand that there will have to be yet another follow-up to this investigation. I will try my best to get that out before the first orbital flight test. With that being said, I highly recommend subscribing to the channel and hitting the alert icon if you haven't already so you don't miss future updates on this situation. Originally, I thought I was going to be able to fully cover this topic in one episode, but that clearly was not the case. We still aren't done explaining what measures SpaceX has taken in order to enable themselves to safely perform a 33-engine static fire on the Orbital Launch Mount. So, in part 3 of this deep dive, we will leave the speculation behind for a while and return to the cold hard facts. In that episode, we will discuss the hidden upgrades that SpaceX has made to the Orbital Launch Mount in order to protect it against the worst case scenario. The one that will occur if all of the measures I've discussed in part 1 and 2 happen to fail for some reason. As morbid as that sounds, this is the Stage 0 feature I am currently the most in love with. A recent addition to the list of top 5 reasons that the Starship Orbital Launch Mount is actually an engineering masterpiece, even though it seems like it's currently riddled with a bunch of issues lately. Of course, I'm referring to one of my favorite subjects here, Orbital Launch Mount shielding. She's been naked for way too long now, and it's time to cover up. So as promised,
if I see any more signs that SpaceX is gonna throw some more clothes on this naked launch mount, I promise I'm gonna be the first ones to let you guys know.
if you enjoyed this episode, let us know by hitting that like button. If you hated it, let us know why in the comments. And make sure you list out every point you disagree with so we can address it during the live stream. For those of you who are returning viewers, if you can't tell by now, we did some major upgrades since the last episode. Elon has been very busy over at Twitter headquarters over the last few months. Now that his huge ass sleeping bag is no longer in the middle of the floor, we were given the clearance to completely renovate this side of the roof bar. It wasn't cheap though, so if you would like to support our German 3D forensics agents who traveled all the way down to Starbase to perform this manual labor, you can do so by becoming a member of the YouTube channel by clicking on this link here or becoming a monthly supporter on Patreon. I want to give a huge shout out to everyone who donated via PayPal for the new camera fund. I chose to wait to the end of this episode to announce that we were finally able to upgrade from the DSLR we were using for all of the green screen work to a significantly higher quality cinema camera. The Sony FX30 is a game changer for us, and we can't wait to show our channel members a behind the scenes look at what it's going to allow us to do. With that being said, if you would like to donate to the ongoing camera fund and contribute to the remaining upgrades that are needed in order for us to maximize its capabilities, you can do so by donating via the PayPal link in the description. As always, I want to give a massive shout out to Lab Padre, NASA Spaceflight, and all of the photographers and 3D forensics agents whose content was used here today. Without them, none of this would be possible. If you would like to support any of these content creators, you can find the links to their various platforms in the description. Also, while you're at it, if you made it this far into the episode, I think you can safely call yourself a Starship addict. With that being said, you should probably download the Starbase Simulator game using this link and give it a try for yourself. I'm not gonna lie, there's a bit of a learning curve, but this game is a great way to get a hands-on learning experience to see how all of this stuff works. And straight up, if you're a substitute science teacher working in a school where all the little shorties have laptops now, this game can occupy their entire day. Anyways, I think my time is up for now, so with that, I'll see you all next time. Stage 0 Zach, signing off.